Okay, in this video, we're going to go through a energy gain function with two food items, an optimal food item and a suboptimal food item in it. In a previous video, I overviewed this primary energy gain function of the optimal food item, how you might plot that. And we plotted it in Excel here, you can see. And we're going to actually use this equation here to get an idea in a food system where there are two foods. This is hypothetical, where one food is the optimal food. It has a higher energy gain than a second suboptimal food. And we're going to use this equation to determine when it might be preferred to be a generalist, so to eat some of the suboptimal food item, and then when it might be more preferred to be a specialist. So that's what this equation can tell you. And so when you look at the output from this equation, given different scenarios, when the result of this equation is higher than the output from a single, from using the same parameters, the optimal food item, then it makes sense to be a generalist. And then when the result of this equation is lower than that from the one food equation, then it's more preferred to be a specialist. And so in the previous video, we plotted this function. We put in some scenarios, scenario 1 through 10, of the optimal food item, which we assigned a value of 10 for energy, the area searched being 1, the population density ranging from 0.1 to 1 in that per unit area, and the handling time being 4. So let's actually generate 10 scenarios as well for a system with an additional food item that's not as optimal. Okay, and so I'm going to assign suboptimal as a food item that has a lower energy value. We're also going to be changing this column here, the population density of the food item. But the one thing that's different about the actual food item is its energy value. It's going to have a lower energy value. We're going to give it half the energy value. Instead of having an energy value of 10, we're going to give it an energy value of 5. And we can copy paste that in. The area searched is going to stay the same. Okay, it's going to be 1. Let's say it's 1 hectare. Okay. Now we're going to change this to have the food item be very abundant. So this is an item that is suboptimal. It wouldn't be preferred in the environment, but when this item might be rare and this item is abundant, I'm curious to see how the equation changes with the change in population density. So I'm going to start this one at being pretty abundant and going to being very, very abundant. So all the way from 1, so 10 times higher starting out than the preferred food item, the optimal food item, all the way up to 10. Okay. Handling time, we're going to keep the same. So it's a similar kind of food item. It just does not have the same energy content, but it's much more abundant in the environment. Okay. So you can actually take this same equation for which is here. These equations, what we're showing you here for top and bottom is this equation, the energy gain function. And we can put an energy gain function in here. In fact, we can probably copy and paste this, this equation here. We'd want to double check, but we can probably copy paste it right into the same set of cells. We just want to double check that it's taking the same values, which is E, and that's B15, C15, and D15. And same here, that it's 1 plus area, which is C15, times handling time, which is E15, times density, which is D15. Yes. And then we would actually want to plot, oh, I see, I need to get rid of this one in this case. We want to divide the top by the bottom, which is, again, it's done it correctly. So we can plot an energy gain function for these same variables. And you can see here, you could compare these two energy gain functions. And remembering, this is a food item that has half the energy available per unit that's consumed. It has a similar handling time, but it's really abundant. And if that energy were fed upon in the environment across a much higher level of abundance, at some point, it doesn't take much before the optimal food item is actually providing a much higher energy gain, even though it's not very abundant in the environment. So it's just something to kind of keep in mind. You can compare these two scenarios here to see how they might look, one compared to the other. But what we want to do is use this equation here, which is the generalist compared to specialist equation. And what we're going to be doing is we're going to make this equation, and then we're going to compare it to this one. This is the equation that we want to compare it with. And I'm going to kind of just highlight it right now as yellow, or maybe we'll highlight it just in a color of something that's, well, maybe I'll just put an outline around it so we can see it. Yellow. So this is what we're going to be comparing. So again, I'm going to use this approach of plugging in the top part of the equation into Excel, then the bottom part, and then dividing by the top. And so I'm going to just call this the generalist equation. Oops. And then for each piece of the equation, I'm going to enter it. So I'm going to enter the top here, the bottom, and then the top divided by the bottom. Okay, so the top is, I'm going to put an equal sign. It's the area. And in both cases, the area is the same. The area searched is the same. Okay. And then we're going to times, and then we're going to do this close parentheses, energy gain of item 1. So we have to be kind of careful here. You have to type in the energy gain of item 1 in scenario 1, which is up here, B2, times the population density of the optimal N1 food item, okay? Plus the energy gain of the second food item here times the energy gain, the population density of this second food item. Okay. And that's the top part of our equation. So for the bottom part of the equation, we're going to do an equal sign, 1 plus, and again, we're going to type in our area. Right here, I'm going to pick my cell again, times, do the parentheses sign. This is where we model in the handling time of the optimal item. So that's up here, times the area of that item, N1, plus the handling time of this suboptimal food item, times, again, the density of that food item. Okay. And so now all that's left is to divide the top by the bottom. Okay. And so now we have a result of this equation here. This is our first result. And what you're comparing this to is the first result to this equation. Okay. And so you're looking in this scenario where the optimal food item is very scarce in abundance. Okay. It's 0.1 per unit area. And the second food item is much more abundant, 1 item per area. Given all the other constraints about it, it has a lower energy value. In that scenario, this result here, which is number 1.1111, okay, I'm highlighting it in gray, is a number that's greater than this number here, 0.714. So in that feeding scenario, it would be favorable to feed on both food items, okay, to feed on the optimal and the suboptimal food item, to invest some energy in that, because the optimal one is not very common. Now let's see if this equation changes once we change how abundant the optimal food item is in the environment. So I'm going to highlight these 3 rows and just drag them down. And I'm going to take off the gray here. And I'm going to put a border around it too, so that I know what I'm comparing. So in this scenario, it would be preferable to be a generalist. Let's look at the second scenario here, where, and maybe what we'll do is we'll line these 2 up next to each other, okay? Hopefully they, I'm going to just paste them in as values here. I'm actually going to just take this right here, the results of this equation here. And I'm going to paste it in right next to this one as values only, not the equations. Okay, so now I'm comparing the function of just the optimal food item to this generalist versus specialist function. In this case, it's going to be better. You're going to be better off being a generalist. Highlight things. So I'm going to put a color, maybe purplish here. Okay. In this next equation, so this is a scenario actually where this very optimal food item is a little bit more abundant. It's still not highly abundant, and the suboptimal food item is even more abundant. It's way more abundant and it's even more abundant. And in this case also, it's preferred to be the generalist. Okay, you should take some of that suboptimal food item. The organism would benefit from that. In this scenario, look at this, it switches. So once you get to 0.3, it makes sense now to be a specialist and just to go for the optimal food item. Even though in this environment, now the suboptimal food item is also even more abundant. And this continues on down. Now that we've reached this sort of threshold of 0.3 and of this optimal food item, it remains beneficial to just prefer the optimal food item now that it has a higher abundance in the environment, even when the suboptimal thing is also more abundant. So if I were to draw a little dotted line, like in this scenario here in the textbook, I could draw a line right at 1.2. Okay, so this would be the threshold, and I'm just going to draw a line in here just so that we can see how it would look in this graph if I want to add a line. Okay, so now I'm going to insert a line right here at, again, at 1.2. So here's 1.5, 1.2 is going to be somewhere right here. So this is our profitability of prey item 2. We could insert that right in here. And so what we're saying is below this threshold right here, it makes sense to be a generalist. But once these 2 lines intersect and the abundance of the optimal item increases, it makes sense to be a specialist. So you can generate the exact same curves you see in the text with a data set if you like to play with Excel and you're curious to test how these models work. And you could also use this as to test some hypothesis in nature about the abundances of optimal and suboptimal food items. You could predict what a threshold might be and then test it to see where it actually is. All right. I hope you had fun with that. I did.